every single time a web page freezes, right? Like when you click a button and the loading spinner just completely stops dead in its tracks.
Oh, yeah, and you find yourself just, furiously rage-clicking the mouse.
Exactly. Well, what you're witnessing right there is basically a microscopic traffic jam. I mean, millions of instructions are suddenly just piling up, waiting for one single, completely overworked lane to clear.
Right, it's total gridlock.
And so today, we are looking at the hidden mechanics behind that exact moment. We're unpacking what separates those frustrating locked-up web pages from the ones that feel incredibly smooth no matter how much heavy data they are crunching in the background. Welcome to the deep dive.
I'm really excited for this one. We are dissecting a sort of narrative-style technical breakdown by Aaron Rose. It's titled The Secret Life of JavaScript Unblocking the UI with Web Workers.
Yeah, and it's a really unique format.
It is, yeah. What makes this material so compelling is how it grounds this really complex browser architecture in a highly atmospheric scenario.
Yep.
Like, it's not a dry manual. We actually follow two developers. There's Margaret, who is a senior software engineer, and her junior colleague, Timothy.
And the setting is wild. They work in this grand, like Victorian library in London.
Exactly. It's an environment of towering oak bookshelves and leather chairs, which it sets a very deliberate tone,
Yeah, it feels like a place where you'd be reading Charles Dickens, not writing code.
Right. But that's the point. Code quality here is not just a passing concern. Craftsmanship and, well, architectural elegance are treated as high-stakes imperatives.
It creates such a great contrast,
Yeah.
between that old-world deliberate craftsmanship and our modern high-speed JavaScript environment.
Absolutely.
And for anyone listening right now, whether you are an engineer actively debugging latency or maybe someone prepping for a technical review, or honestly, just someone who wants to understand why your digital tools behave the way they do, this exploration completely pulls back the curtain.
It really does.
It shows how browsers physically handle heavy workloads. I mean, it will completely change how you look at the interface of every web application you use.
And we can see that dynamic play out immediately with Timothy's predicament. So Timothy has built a dashboard to analyze system logs.
Okay.
And he's utilizing the File System Access API to pull in these massive log strings, specifically a 15-megabyte text file.
Which, I mean, let's pause there because 15 megabytes might not sound massive when we talk about video or audio files.
Right. For a video, that's nothing.
But 15 megabytes of pure string data, that is an enormous payload for a browser to parse sequentially.
It's millions of characters. And so he clicks his Analyze button, and his carefully placed animated loading spinner instantly stops. The entire application just bricks.
It's completely dead.
Completely. For 3 full seconds, he cannot select text, he cannot click other tabs, the page is just frozen.
I hate when that happens.
Right. Then it suddenly snaps back to life, the spinner vanishes, and his error codes finally populate on the screen. He got his result, but the user experience leading up to it was terrible.
Well, and if we think about it, Timothy probably assumes the browser tab is locking up just because the search is running, right?
Oh, that's his first instinct. He's using this really complex, regular expression to extract specific error patterns from that massive string.
Yeah.
Scanning a 15-megabyte continuous string, character by character, holding all these states in memory, and looking for specific sequences, it requires significant CPU cycles.
So if we visualize this, I like to think of it not as a restaurant with a kitchen full of staff.
Yeah.
The JavaScript engine essentially operates as a restaurant with only one incredibly fast chef. And if you ask that single chef to sit in the corner and count 15 million grains of rice...
They can't do anything else.
Exactly. They can't simultaneously stir the soup or greet customers or ring the bell. Everything stops until the rice is counted.
That is a perfect analogy, and that fundamental architectural limitation is exactly what Margaret points out to him. By default, the standard JavaScript environment gives you exactly one thread of execution, the main thread.
The one chef.
The one chef. When Timothy asks that thread to evaluate his dense, regular expression, he is basically parking a massive, slow-moving semi-truck in that single lane.
Which means nothing else can get by. But what is actually trying to get by during those 3 seconds? I mean, we know the math is running, but what else is that single thread responsible for?
Literally everything.
Really?
Everything.
Everything. That single thread evaluates the JavaScript, sure, but it also listens for user interactions like clicks and scrolls. And critically, it is responsible for the rendering pipeline.
Oh, right. The visual stuff.
Yeah. To make an animation like a loading spinner look smooth, the browser needs to calculate styles, figure out the layout, and paint new pixels to the screen. And it ideally wants to do this 60 times per second.
Wow, 60 times. Yeah, so that gives the thread about 16 milliseconds to complete any given task before it needs to paint the next frame.
Okay, so if the thread is trapped inside a regular expression that takes 3 full seconds to resolve, it completely misses, what, hundreds of painting deadlines?
Hundreds of them. It cannot paint the next frame of the spinner. It cannot register the mouse click trying to highlight text. The UI is not just running slowly, it is entirely blocked until that regular expression finishes and frees up the call stack.
So Timothy's initial instinct, naturally, is probably to try and write a faster query, right?
Oh, of course.
Like, he wants to look into hyper-optimizing his regular expression.
Yeah.
Maybe checking for catastrophic backtracking or restructuring his search patterns.
Which is a very common junior impulse, honestly, to try and outmath a fundamentally heavy operation.
Right.
But Margaret steps in with a totally different perspective. She points out that if a computation is intrinsically heavy, optimizing the algorithm only delays the inevitable.
Because the data is always going to grow.
Exactly. If the file grows from 15 megabytes to 50 megabytes next week, the optimized regex will still freeze the UI eventually. The solution requires a paradigm shift. You have to move the processing out of the main thread entirely.
So she steps over to the whiteboard in this beautiful Victorian library and introduces the Web Workers API, specifically the new worker command.
Yes.
And she explains that they can spin up a complete and separate, isolated background thread.
Right, which shifts the browser from behaving like a single-lane road to a multi-lane highway. The main thread can continue handling the UI, painting the screen at 60 frames per second, while the new background thread handles the heavy string parsing.
But wait, I have to ask, because I know people listening are wondering this too.
Sure.
If we have the power to spin up this separate thread, and it is the one actually finding the error codes, why pipe the results back to the main thread?
What do you mean?
Like, why not just have the background worker print those error codes directly to the DOM and stop the loading spinner itself to save the trip? Keep the chef in the back kitchen, do everything.
Well, the browser physically will not allow it.
Really? Why not?
If you look at the underlying memory architecture of a browser, the document object model, the DOM, is not just a static text file. It is a highly optimized, living graphical state machine.
Okay.
Allowing multiple threads to manipulate that exact same visual interface concurrently creates what we call race conditions.
Meaning like two threads trying to change the exact same pixel at the exact same time.
Exactly. Or, for example, one thread trying to delete a table row while a background thread is simultaneously trying to change the text color of that row.
Oh, yeah, that would be a mess.
It would crash. In lower-level programming languages, you solve this with locks, where a thread temporarily locks a piece of memory so nothing else can touch it.
Right.
But locking and unlocking nodes in the render tree constantly would destroy the browser's ability to render at 60 frames per second. It's just too much overhead.
So they just forbid it.
Yeah, browser vendors made a blanket rule. Background workers have absolutely zero access to the DOM. They live in a completely isolated environment.
Wow, okay. So if they are entirely cut off from the DOM, they need a way to communicate with the main thread.
Yes.
How do they actually exchange that 15 megabyte file and the resulting error codes?
They use a secure asynchronous messaging system called postmessage. Think of it like a pneumatic tube system between the front desk and a secure vault.
Okay, I love that image.
Right. The main thread takes the massive log file and sends a message containing it down the tube.
And it is important to note here, the browser isn't just handing the worker a reference to the file in memory, right?
Correct.
It uses something called the structured clone algorithm to actually serialize the data, send a copy down the tube, and deserialize it on the other side.
Which means there is a slight computational cost to the messaging itself.
Right.
But once the worker receives that data, it crunches the regular expression on its own time. The main thread immediately goes back to painting the loading spinner and listening for user clicks.
The chef is back to stirring the soup.
Exactly. And whenever the worker finishes, whether it takes 3 seconds or 30 seconds, it packages the extracted error codes into a new message, sends it back up the tube, and triggers an event on the main thread.
And then the main thread updates the DOM.
That's right.
Okay, so that is the concept on the whiteboard. But moving from the whiteboard concept to the actual code base introduces a whole new set of challenges, doesn't it?
Oh, definitely.
Getting a worker to function is one thing, but making the implementation resilient and memory efficient requires a different level of engineering, like junior versus senior execution.
Yes, and that is where Margaret gives Timothy specific architectural rules regarding lifecycle management. starting with the overhead of the worker itself.
Because it's not free to make one.
No, calling new worker is not a free operation. The browser has to allocate fresh memory, spin up a new V8 JavaScript isolate, and build a whole new execution context.
So if Timothy's application destroys the worker after every single search and creates a brand new one the next time the user clicks Analyze, he is introducing terrible latency.
He is paying the startup cost over and over again. It completely defeats the purpose.
Right. So the strategy is to instantiate the worker once when the application or component loads, and then keep it alive as a dedicated parsing engine that just sits there waiting for messages.
Precisely. You pool your resources, you keep the thread alive, and simply reuse it for subsequent searches during that user session.
But keeping a thread alive indefinitely introduces a massive risk for memory leaks.
Oh, a huge risk.
Because if you open a dashboard, spin up a dedicated worker thread, and then navigate away to a different part of the application without cleaning up, that background thread is still sitting in memory, holding on to whatever data it last processed.
Exactly. And modern web frameworks with component-based architectures make this especially dangerous.
How so?
Well, when a component unmounts from the screen, developers often forget that the background worker they spawned does not automatically die with it. It's a completely separate thread.
Out of sight, out of mind.
Yes. So Margaret insists on strict memory management. You have to explicitly call the worker.terminate command when the host component is destroyed. You have to manage the thread's life cycle deliberately from creation to garbage collection.
That makes total sense. Now, there's another safety net Margaret enforces, which deals with what happens inside the worker while it is actually running.
Right, the error handling.
Yeah, she says the background execution must be wrapped in a try-catch block.
This is critical because if we send a massive log string down the tube and the regular expression fails, maybe the string is malformed or it hits some weird edge case, the background thread will throw an error.
And without a try-catch block to handle that error, the background thread just silently dies in its isolated environment.
It just crashes and burns in the vault and no one knows.
And if it silently dies, it never sends a message back up the tube. The main thread, which is eagerly anticipating a response to resolve the pending state, will just wait indefinitely.
Which means the user is left staring at a loading spitter that will literally animate until the end of time because the main thread does not know the worker crashed.
It's like giving our isolated background chef a two-way radio. If something catches on fire in the back kitchen, like the rejects fails, they need to be able to radio the front of the house so the customer isn't left waiting forever.
Exactly. The isolated thread needs a mechanism to report its own failure. Wrapping the logic in a try-catch block ensures that if an exception occurs, the worker catches it and sends an explicit error message back to the main thread.
And then the main thread can gracefully recover.
Right. It can kill the loading spinner, reset the UI, and display an error message to the user explaining what went wrong. Defensive programming is completely non-negotiable when you start dealing with asynchronous multi-threaded architectures.
Okay, so Timothy takes all of these architectural rules and applies them to his code base.
He does.
He takes his dense parsing logic out of the main execution file and moves it into a dedicated analyzer worker.js file. He refactors the dashboard to instantiate the worker once, sets up the post-message communication pipeline, and implements the error boundaries so the main thread always knows the status of the background task.
He stops fighting the limitations of the single-threaded environment and finally utilizes the tools designed to bypass it.
And the payoff is amazing. He saves his files, reloads the dashboard, and clicks Analyze.
Yeah.
This time, the animation on the loading spinner is completely fluid. He can click and drag his mouse over the text on the page, and the browser highlights it without dropping a single frame. He can interact with other tabs seamlessly.
That's the dream.
3 seconds later, the background worker finishes the heavy string parsing, pipes the data back to the main thread, and the grid populates with the error codes. The application feels incredibly responsive.
Because the visual feedback is no longer tied to the computational load. The interface remains interactive regardless of how intensely the CPU is working behind the scenes.
It's such a great journey. I mean, we started with a junior developer staring at a frozen screen in a Victorian library because he was forcing one single lane of traffic to handle everything.
Right.
But by recognizing the architectural constraints of the browser, offloading the heavy string, parsing to an isolated thread, and rigorously managing the memory lifecycle, we end up with a highly resilient application.
It's a complete transformation.
So for you listening, the next time you are using a web-based data visualization tool or a massive spreadsheet application and it remains perfectly interactive while crunching data, you know there is a web worker quietly handling the heavy lifting behind the scenes.
And the evolution of these mechanics opens up a much broader, almost philosophical conversation about where web infrastructure is heading.
Oh, tell me more.
Well, we just explored how a single background thread can save a UI from freezing while processing a 15-megabyte text file, right?
Yeah.
But modern web applications are scaling exponentially. We are seeing full, nonlinear video editing software running entirely in the browser.
Which is crazy to think about.
It is. We have real-time 3D rendering engines and complex artificial intelligence models processing locally without ever talking to a server.
Wow.
So it begs the question, at what point does a web application stop needing just one background worker and start requiring an entire army of threads communicating via shared memory buffers?
Oh, wow.
And if individual browser tabs are now spinning up their own complex networks of background threads, managing resource allocation and handling memory garbage collection, are our internet browsers slowly evolving into fully fledged operating systems right before our eyes?
From a simple frozen loading spinner to the browser, absorbing the responsibilities of the operating system, that is a massive shift to think about the next time you open a new tab. Thank you for joining us on this deep dive. We hope you walk away with a clear understanding of the hidden traffic controlling your screen. Take care.